effect of finite number of veins on Euler head. So till now our assumption is in an impeller we have infinite number of veins. So accordingly we develop a formula for Euler head of a centrifugal pump. So now we see if we have a finite number of veins in the impeller, so then what is its effect on the Euler's head? Okay, so now see we have in this diagram, now in this diagram we have the impeller. So in impeller we have a vein. So in vein we have a passage. So this is the passage from where the water flows from inner side to the outward side. Now when we have the infinite number of veins, then the velocity distribution is uniform, that you can see in this diagram. So here the velocity distribution is, you can see it is uniform. Okay, so this is the velocity distribution when we have infinite number of veins. Okay, we have finite number of veins. Now in that case, now due to inertia, the liquid particles are reluctant to turn with the impeller. Okay, so this results in a high pressure on the loading surface of the vein and low or less pressure on the back face. Now you can see in this diagram, now this is the passage through which the water goes through the impeller. So this is the one side of one vein. Okay, this is the another side of another vein. So through these two veins, the water passes from inner side to the outward side. Then you can see here when this impeller rotates in this direction, this is the direction of rotation for the impeller. Now you can see due to inertia, here is the more pressure on this face of the vein. On the other face of the vein, you can see on other vein, we have somewhat less pressure. Now due to this pressure variation, now where the pressure is more, velocity is less. Where pressure is less, velocity is more. So then the velocity distribution is something like this. Okay, on this side we have low velocity and here we have the higher velocity. So that is varies from minimum from this side to maximum on other side. Okay, so this is the velocity distribution due to pressure distribution when we have finite number of veins. Now this impact on the motion of water going from inner side to the outer side of the impeller. Okay, so due to this now, when there is pressure variation, there is a velocity variation. So the water going out something like this. Okay, it is in rotation and moving in the outward direction. Okay. Now circulation, this circulation you can see, okay. Now the direction of this circulation is opposite to the motion of the impeller. Now you can see here the impeller rotates in anti-clockwise direction. However, the rotation of the moving fluid is along the clockwise direction and in the forward direction also. Okay. So due to this circulation, now there is the effect on the velocity diagram. Okay, the velocity diagram at the outlet of the impeller. Okay, the impact is now, you can see, now we have the velocity diagram, the initial velocity diagram, that is this one with thick lines. Okay, now this is VO and this is VRO and the angle is beta O dash. This angle is beta O dash. This one is tangential velocity UO at the outlet. Okay, and this one is the VWO, whirl component of velocity at the outlet. So this red diagram is for when we have infinite number of vanes. Now when we have finite number of vanes, due to this rotation, there is reduction in beta O dash to say beta O. Now you can see in this diagram, there is reduction in this beta O dash to beta O. And my new relative velocity at outlet is VRO dash. So my beta O dash reduces to beta O. Okay. Now my pump is rotating at constant speed. So therefore, my UO is equal to UO dash, means either we have finite number of vanes or infinite number of vanes. My speed of the pump is constant. So therefore, UO is equal to UO dash for infinite number of vanes, and for finite number of vanes, the value of UO is same. So now from here, you can see, now this is my UO dash. So this is my UO dash. Okay. Now UO dash is equal to UO. So from here, I cut this line equal to UO for constant speed. Okay. So then this is my new VO. That becomes VO dash. So my green triangle is for finite number of vanes with new beta O dash. Now you can see what is the effect of this on whirl component of velocity. Now this is now VWO dash. Okay. So for infinite number of vanes, my whirl component is VWO for infinite number of vanes, and for finite number of vanes, my whirl component is VWO dash. Okay. Now the difference of these two. Now the difference of these two is called slip. The difference of these two is called slip. So you can write here now slip is equal to VWO minus VWO dash. Now this is this shift. Okay. The slip is the shift of VWO to VWO dash. The new whirl component of velocity at the outlet. Now this effect on the Euler head also. So then my new Euler's head for finite number of vanes is equal to VWO dash UO divided by G. Okay. Otherwise it is for infinite number of vanes it is HE is equal to VWO UO divided by G. Okay. Now the ratio of HE dash to HE, this is mu. Now this is called vane coefficient. This is vane coefficient. Okay. So mu is equal to HE dash upon HE. Or this is also equal to VWO dash upon VWO. Okay. The empirical relation for this mu is 1 divided by 1 plus 2 RO square phi Z RO square minus RI square. Okay. So where phi is, the phi is equal to 0.60 plus 0.6 sine of beta O dash. That is phi. Okay. And Z is the number of vanes. Okay. RO is the radius of impeller at the outlet and Ri is the radius of impeller at the inlet. Okay, so this gives me the value of mu, that is vane coefficient. Okay, so this is the effect of finite number of vanes on Euler's head. Then next I have various losses and efficiencies. The first one is the hydraulic efficiency. Okay, now the hydraulic losses. So this hydraulic efficiency accounts the hydraulic losses. So this accounts the hydraulic losses. So that are the losses occurs between the suction and the delivery ends of a pump. Okay. So whatever the losses occurs between the suction side and the delivery side of the pump, the total losses are the hydraulic losses. So these losses includes the shock loss at the entrance of the impeller, the friction and eddy loss in the vanes and the casing. Okay, it includes the shock loss at the entrance. It includes friction and eddy loss. in the vanes and casing. Okay. Then further, friction and eddy loss in the suction and delivery pipe. Okay. Then loss due to sudden change in area and direction of flow. Okay. Loss due to sudden change in area of flow. So all such losses occurs in the impeller from suction to delivery side. So that are the hydraulic losses, and all those losses are accounts in hydraulic efficiency. Okay, so hydraulic efficiency can be defined as, this is eta H, defined as the ratio of actual or total head developed head developed divided by the input head of the pump. Okay, so you can say it is the ratio of actual or total head developed and the input head of the pump. So eta H for finite number of vanes, you can write it as H divided by HE dash. Okay, or this becomes equal to GH upon VWO dash UO. Now if Vs is equal to Vd, velocity in suction pipe is equal to velocity in delivery pipe. So my H is approximately equal to Hm. Okay, so I can also write hydraulic efficiency as equal to GHM divided by VWO dash upon UO. And its range is from 0.6 to 0.9. 60% to 90% is the range for hydraulic efficiency. The next is the manometric efficiency. The manometric efficiency is the uh, hydraulic efficiency of the ideal pump. Ideal pump means a pump with infinite number of vanes. So I can write eta MAN manometric to H divided by HE. Okay, this is equal to GHM divided by VWO UO. So this is the hydraulic efficiency of the ideal pump. Ideal pump is the pump with infinite number of vanes. Okay, so I can also write eta MAN is equal to H upon HE, that is equal to hydraulic efficiency into HE dash upon HE. Okay, or I can write it as hydraulic efficiency into mu HE upon HE. So HE cancels with each other. So equal to mu times eta H. So eta manometric is also equal to mu times eta H. Another relation for manometric efficiency. Okay. So when mu is equal to 1, okay, hydraulic efficiency becomes equal to manometric efficiency. The next is the volumetric efficiency. Okay, so the volumetric efficiency taken into account the leakage loss. Okay, so there is always a tendency on the part of water slip back or leak back through the clearance between the impeller and the casing. Okay, so there can also be some leakage loss from the seals. Okay, so all these leakage loss we call as the volumetric losses. So my volumetric efficiency is eta V, that is equal to the ratio of actual discharge to the total discharge. Okay, actual discharge to the total discharge. So that I can write as Q divided by Q plus delta Q. Okay, so Q plus delta Q is the total discharge. Okay, or you can say this is the amount of water supplied to the pump. The amount of water supplied to the pump. Okay, and Q is the actual discharge at the outlet, and delta Q is the leakage loss. Okay, so that is my volumetric efficiency, and the range for volumetric efficiency is from 0.97 to, or you can say 0.95 to 0.98. The next is the mechanical efficiency. So this efficiency accounts all the mechanical losses in the pump. So those mechanical losses are due to friction in bearing, that is the due to disc friction or wind friction. Okay, so the disc friction or wind friction is uh, within the impeller when that impeller rotates in a liquid. Okay, impeller rotates in a liquid. So that liquid, due to viscosity of that liquid, there is some resistance to the rotation of the impeller. So that is my disc or wind friction. So that is one type of mechanical loss. Okay, so my mechanical efficiency eta M, that I can write as P minus delta P divided by P. So P is my total power input to the shaft. P is the total power input to the shaft, and delta P is my mechanical losses. Okay, and this range is again from 95 to 98%. Okay, and the last efficiency is the overall efficiency. So that accounts all the losses in the centrifugal pump, and it is the ratio of head developed, total head developed by a pump to the total power input to the shaft. So I can write my eta O, that is equal to WQH divided by P. Okay. Now further I can write this as, so rho W I can write as rho G. Okay. So this I can write as H divided by VWO dash UO divided by G. Okay. Into Q upon Q plus delta Q into rho Q plus delta Q VWO dash UO divided by P. So that is eta O is equal to, now this is my hydraulic efficiency, okay, into volumetric efficiency into mechanical efficiency. Okay, so when the number of vanes are infinite, when the number of vanes are infinite, so my eta H is equal to eta MAN, manometric. So I can write overall efficiency H upon VWO UO upon G into Q upon Q plus delta Q into rho Q plus delta Q into VWO UO divided by G. Okay, so that is my hydraulic efficiency, oh sorry, overall efficiency is equal to eta manometric efficiency into eta V into eta M. Okay, so the range of overall efficiency for a centrifugal pump is from 0.71 to 0.86, that is 71% to 86%. Okay, so these are the various losses and efficiencies in the centrifugal pump.